How you doing? I hope you had a good day. We are in Volume 2, Chapter 2 of the Sacramento State series. And we're going to talk about nutrient removal. The EPA has, in the last couple of years, have really started thinking about, phosphorus limits and, how we are going to make sure that we're not discharging nutrients to our bodies of water that is below our plant. And when we talk about nutrients, mainly we're talking about uh, nitrogen, and we're also talking about phosphorus. On page 48, it says Kendo nitrogen, or TKM, which is nitrogen in the form of organic proteins or their decomposition product, ammonia, plus the oxidized forms of nitrogen. So, it encompasses ammonia and the oxidized form of nitrogen. So, at my plant, 3 times a week, we test the ammonia going out. Obviously, if you've ever had a fish tank, you know that ammonia can be toxic to aquatic life. Um, so that is one parameter that we keep a close eye on and report to EPA. The other thing that we do is phosphorus. The phosphorus is measured as either total phosphorus or orthophosphorus. Now, you kind of think well, total phosphorus, orthophosphorus, but orthophosphorus is often used to estimate the available phosphorus for the biological process, right? So I know at our plant, we take a sample, we strain it, and we send our orthophosphate out to a contract laboratory, and they run our ortho, and then we report that to the EPA. As I know, we do not have a phosphorus limit. Um, there has been talks over the years about having a phosphorus limit, but one of the reasons why we don't want an algae bloom to happen, because if an algae bloom happens downstream, when that algae plant dies, it's going to decompose and it's going to take up oxygen. And as we know, that oxygen removal is harmful to aquatic life. This is important. I've seen this on a test, but during aerobic wastewater treatment, the CMP ratio should be somewhere between 110 and 105 to 1. And so that's your carbon, nitrogen, and phosphorus ratio. One reason, one way that we get rid of phosphorus is either aerobically and anaerobically, or we can add chemicals to for the phosphorus to settle out once it adheres to some sort of chemical that we add, and then we can remove it in the sludge process. We're going to talk about those later on in our system. Let's talk about nitrification. So, we've talked a lot in my videos about the nitrification, denitrification, and really we're trying to convert that ammonia over to be released into the atmosphere as nitrogen gas instead of um, discharging to our plant. But nitrification is the biological process accomplished primarily by two types of microorganisms. Uh, it says ammonia oxidizing bacteria and nitrite oxidizing bacteria. These are autotrophic. Now, I have had this on a test question. You need to know the difference between autotrophic and heterotrophic. Autotrophic are organisms that use inorganic materials such as sunlight and carbon dioxide for their energy and growth. So we want these autotrophic bacteria to work on the ammonia. Okay. Heterotrophic are organisms that use organic matter for their energy and growth. Um, Animals, fungi, and most bacteria are heterotrophic. So your organic matter, whatever your food waste that go down your garbage disposal, That is your um, heterotrophic bacteria that will feast on that. The first step in nitrification process is the conversion of ammonia to nitrite. The second is the conversion of nitrite to nitrate, and then proper conditions must exist to separate the nitrogen from the hydrogen in the ammonia molecule and replace the hydrogen with oxygen molecules. So we talk about our first step of uh, nitrification, and then the second step would be uh, denitrification. But as you can see on page 53, it does take ammonia or alkalinity for ammonia. The process consumes some alkalinity, and so you need that alkalinity in your water. Alkalinity is a measure of the substances in the water to buffer acid, and I believe it's down to 4.5. Let's talk about um, these two definitions, suspended growth and attached growth. We've talked about this before, but I just want to highlight this so you know when you go in to take your test. Obviously, the suspended growth is in your aeration tank. Your attached growth would be in like your fixed film in your RBCs and those type of treatment systems. I know I'm kind of rehashing some of these things, but hopefully between me rehashing them that they'll remember. On page 57, nitrogen is removed by modifying the activated sludge process to include separate tanks or zones within the tanks to produce a sequence of anaerobic, anoxic, and aerobic environments by applying or preventing aeration. The goal is to create favorable environments in which the appropriate microorganisms convert the nitrogen into a form that can be removed from the wastewater being treated. It tells you the different ways that you can do that in like a conventional plug aeration system, a complete mix, activated sludge process, a contact stabilization, step feed, extended, and you can read on to that. Um, I would like to highlight on page 58, bottom paragraph, because nitrifying bacteria grows so much slower than carbon oxidized bacteria. Any conditions with high BOD concentration will provide an environment where carbon oxidized bacteria will always outcompete nitrifying bacteria. I had someone tell me, um, if typically, and this is not all the way across the board, but if you have a low ammonia, and you have standard domestic waste coming into your plant, if you have low ammonia, you probably are going to have a good BOD, because BOD needs to be, which I just read, you know, that bacteria needs to have its predominance before ammonia really can really take place. Now, obviously, that's not a golden rule that you can stand by, depending on what your makeup of your collection system is and who's discharging, right? But in your typical bedroom community that you're treating, that's going to be true. So I know the problem with BOD is it's a 5-day test. But if you see your ammonia start creeping up, at least at my facility, if you see your ammonia start creeping up, you probably can suspect that you have something going on with your BOD also. It's a good indicator, anyhow. Uh, and ammonia is so easy to test. We have test strips. Now, that's not reportable to the EPA, but testing your ammonia in your different clarifiers and your different tanks, it's an invaluable tool to really keep your, I guess, finger on the pulse of all of the plant. So when we talk about alkalinity, I've worked with the EPA and they've tested the alkalinity of my water coming in to my wastewater because alkalinity changes in the nitrification process, stream, and final effluent. Um, you know, as I said, and this is on page 60, 61, you're going to have um, alkalinity consumed uh, in that nitrification system. So you have to have it um, there for the removal of ammonia. Um, on 63, generally, at least 50 milligrams of alkalinity should remain after nitrification. Nitrifiers have been met all their alkalinity requirements to minimize a pH drop. And you can read on about, um, you know, alkalinity and its role in the wastewater system. Going over to page 66. So on 66, we have nitrification using fixed film reactors. Those are your trickling filters, your pack towers, anything, the system where it is on page 67, it's dropping the water through either rock media in the trickling filter or plastic media. And as it does its zigzag, it's picking up air. There's vents in the system and it's picking up air. There's biological growth growing on those rocks or that media and helping remove ammonia. RBCs, rotating biological contactors, those are also can be used. That biofilm that grows on those can also be used for the removal of ammonia. We need to know our hydraulic loading and our organic loading, right? Um, we also need to know that temperature is under control. So if it's really cold, your your ammonia process may slow down. Just it says on page 71, it says nitrification bacteria tends to slow down and become inactive when wastewater temperatures drop below 50 Fahrenheit. Um, it has some troubleshooting denitrification. So let's talk about denitrification. Is accomplished using fixed film denitrification, such as a trickling filter or rotating biological uh, contactor. Microorganisms reduce nitrate to nitrogen gas and then release it into the atmosphere. And that's really what we want to happen. And usually we have that happen, I believe, in the aerobic, or not aerobic, the anoxic zones. We really want to create those zones where there's little to no air, or some, but little to no air, so that it can be released. And so I've shared with you at my work, I have a suspended growth. We add air to the mixed liquor, and once again, there are parts of the tank that are highly oxygenated, and then there are other parts that just kind of at a slow moving. And the reason why is because we don't want denitrification to happen in our clarifier. Ammonia stripping on page 80. Ammonia stripping is a physical process used to remove nitrogen. Ammonia nitrogen in gaseous form, and only in gaseous form, has a natural tendency to leave water and enter the atmosphere. So, we can add air, we can strip ammonia. Air stripping relies on these concepts by increasing the pH and converting the ammonium to ammonia, then allowing the gas to volatilize. The ammonia is removed from the water. So you can airstrip ammonia. Um, you can do breakpoint chlorination. So you can add chlorination. But as I remember, um, well, and on page 84 at the bottom, it says, while this method can remove ammonia in wastewater, it requires a large amount um, to complete this action, anywhere from 8 to 10 times more chlorine than the ammonia concentration. So you can add more chlorine than ammonia, but usually it's not cost effective. Um, Usually, at least from what I've found, is you're better to do it through your anaerobic and aerobic zones than to try to chlorinate it and then obviously you would have to dechlor it. Ion exchange, ion exchange is zeolite media into a softener. So it's basically your home water softener, but on a huge scale, and we can remove um, ammonia from that and nitrites, from drinking water. But we can use that same process of running the water through there and then regenerating with a salt brine to get rid of ammonia. Phosphorus removal. So phosphorus removal provides a nutrient of food source for algae. Um, Once again, we don't want algae to flourish, receiving waters. Uh, Phosphorus must be, and this is on the bottom of page 89, phosphorus must be in a particulate form so that it can be removed from the wastewater using a physical process like sedimentation or filtration. Since most of total phosphorus is soluble, it must be converted to a particulate form using the biological processes, chemical addition, or a combination of these two methods for effective removal. So if phosphorus is soluble, it's in this, you could say it's in this water, and we want to either use biological or a combination of biological or we would add some sort of chemical to that to create it to a soluble form. And that way we can remove it through either the solid settling or could run it through like a sand filter or a gravity filter, whatever we want to do. Um, so on page 93, you can kind of see like a mainstream process there. It has this anaerobic selector, your reactor, and your sedimentation tank. On your bottom, your side stream, they're using lime precipitation along with an anaerobic stripper. I know we've talked about at our plant possibly having to feed lime if they go to a phosphorus removal or a phosphorus limit, just from the lack of space for another aeration tank or anoxic or anaerobic tank. So one problem with adding lime, obviously it's a chemical, but one problem with adding lime is it just increases more biosolids. So you're gonna have more sludge that you're going to deal with. Luxury uptake of phosphorus. I've had test questions on it, and it's usually a homework question, but luxury uptake of phosphorus is a modification of the basic activated sludge treatment process. When the microorganisms are in a state of endogenous respiration or they're hungry and need food and oxygen, they tend to absorb phosphorus in excess freely. This process is called luxury uptake, in which the microorganisms can take excess phosphorus into their bodies due to the stimulation of being placed in the proper environment containing food and oxygen. When these same organisms are placed in an environment with no oxygen, anaerobic exist, the first element that is released by the microorganisms as they begin to die off is the phosphorus. So really in that anaerobic zone, we've seen um, in the charts before, that's where they really release that phosphorus and then are put back into the tank where it's aerobic. On page 96 and 97, you can see, um, once again, they are um, using anaerobic phosphorus release. They're using a lime slurry to mix with it. Um, you know, drawing the sludge off of a chemical clarifier. On here, you have another. I believe they're using lime and an anaerobic phosphorus release tank. So it's really when those microorganisms have consumed phosphorus, then they go into an anaerobic tank or or zone, and then they can release that phosphorus. Moving right along. So chemical phosphorus removal on page 107. Phosphorus is removed chemically by absorption onto a metal hydroxide flock surface or precipitation of a solid formed by a chemical reaction with phosphate. Absorption involves the binding of phosphate to a metal hydroxide flock. So once again, we are we were trying to remove phosphorus with chemicals. On page 107, we have aluminum sulfate and ferric chloride react with orthophosphorus to form an insoluble precipitates that are removed from the wastewater. Um, you can kind of see on page 109, you have your rapid mix, your alum is added, it flocks, forms to a um, bigger particle that is not soluble and then can settle out in your clarifier. If we can make something flock together and settle out, then we can remove it from the process. On page 110, on the bottom, ferric chloride is the most effective at removing phosphorus when the pH of the wastewater remains between 3.5 and 7. Ferric uh, chloride can provide additional benefits not realized when alum is used. For example, ferric chloride can reduce uh, odors when used with phosphorus from raw influent. Additionally, ferric sludge is more easy dewatered, which means you can get the water off of it than alum sludge. So just kind of one of those points to point out. Obviously, anytime you're dealing with a chemical, you're going to want to follow the safety precautions. Um, you know, I'm not 100% sure on all these, but I just want everybody, possibly wearing a respirator. Check your SDS sheet, but any chemical that, I mean, for me personally, any chemical that you're breathing in, you need to wear a respirator and you need to have that fit tested. Lime precipitation, so adding lime on page 116. When lime is mixed with the effluent from a wastewater treatment in sufficient concentrations to bring about a high pH level in the water, a chemical compound is formed consisting of phosphorus, calcium, and hydroxyl ions. These compounds can be flocculated or combined in such a way to form a heavier soluble uh, solids that can settle out. So we need to know the difference. So when we talk about coagulation, flocculation, and sedimentation, you need to know these, whether you're in drinking water or wastewater side. So coagulation is when chemicals are added to wastewater, the results may be the reduction and electrostatic charges that tend to keep the suspended particles apart. After this chemical addition, the electrical charges on the particles is altered so that the suspended particles containing phosphorus tend to come together rather than remain apart. Flocculation always occurs after coagulation and consists of a collection or agglomeration of the suspended materials into a larger particle. And then obviously sedimentation, which you know. So you always have coagulation, flocculation, um, and then sedimentation. Keep going. Um, on 119, recarbonation. So effluent from a high chemical clarifier used for phosphorus reduction will usually have a pH of 11. So you add all this lime um, or chemical, your pH is going to be super high, and so we'll have to recarbonate to bring that pH back down so that we can release into the environment. Let's see here on page 130, the Bardino process. So, I'd like to go over with you on this. This is kind of the way my plant works. Um, we have an anoxic zone, and then the aeration bank, and then another oxic zone, and then another aeration bank. And then, you can have another zone where you even have anaerobic, you know. So, that when they talk about the Bardino process, that's just the adding of anoxic zones or anaerobic zones and aerobic zones, just so that we can get that full release of either ammonia or whatever other um, we're trying to release. SBRs, we've talked about that. It's a good picture of an SBR. Um, so, you have your influent, your anaerobic mix, then your aerobic, then your anoxic, and then your settling and your withdrawal. So, uh, I actually didn't know that SBRs could be used for nitrogen and phosphorus removal, but it does make sense. Any tanks that we can use, to create that, um, those zones is important for removal of nutrients. On page 143, that's an anoxic zone with a submerged baffle and turbine mixer. I'll give you an idea of one of those. And that's the end. I hope you enjoyed. Maybe we'll make more videos on nutrient removal, but I appreciate you watching. Thank you. Bye.